Have you ever noticed how a magnet can actually make a compass needle spin? As I rotate the permanent magnet armature from this little synchronous motor, the compass follows it exactly, locked in step. Here's how I got to this armature, by the way. This is a teardown of that permanent magnet synchronous motor, the kind you'll find in appliances like timers and dishwasher motors. In a synchronous motor, the motor locks in step with the rotating magnetic field. That's what synchronous means. The rotor speed is directly tied to line frequency. In fact, if I connect a small DC voltage to this motor, the armature locks in one direction. If I reverse the polarity, though, it takes a half a turn, or 180 degrees. That shows how the magnetic poles in the rotor and stator naturally align, the same principle the AC field uses to keep it synchronized. At its operating frequency of 60 Hz, this two-pole synchronous motor runs exactly at 3,600 revolutions per minute, with no slip at all. By contrast, an induction motor, like this refrigerator evaporator fan motor, needs that thing called slip to generate torque, so its rotor speed lags slightly behind the rotating magnetic field. The line frequency sets the upper limit, but the induction motor never quite keeps up. See my full video number 43 on this channel for more about how induction motors work. Now let's take a look inside the stator. You'll see this small notch. That's not a manufacturing defect, it's there on purpose. Some synchronous motors include shaded poles like this one, while others use notches or asymmetries in the stator to influence the starting direction. The goal is to create just enough phase shift in the magnetic field to give the rotor a gentle push in one direction. Without some method like that, a shaded pole, a notch, or other directional cue, a permanent magnet rotor would simply rock back and forth at 60 cycles per second, never deciding on which way to go. Or it may start in an unspecified direction, which simply isn't going to work for many applications. A shaded pole motor uses a copper shading ring for the same reason, to bias the magnetic field slightly in one direction to create a weak rotating field. That's how shaded pole evaporator fan motors start turning reliably every time. This particular synchronous motor may use its stator notch to promote directionality, but that isn't always the case for every design. Some rely on other asymmetries, such as those in the rotor magnets themselves. Once the rotor is spinning, the rotor's inertia helps maintain its direction through each cycle of the AC waveform. It stays phase locked to the stator's magnetic field, kind of like gears meshing perfectly in time. Given that this motor is truly unidirectional, I can flip the stator assembly upside down and the motor should reverse direction, because that changes how the stator's asymmetry interacts with the field. That's similar to flipping the armature on a shaded pole evaporator motor, where changing which side of the shading ring leads the field, determining the direction of rotation. So to recap, a permanent magnet synchronous motor runs locked to line frequency. It won't start in a predictable direction without some directional influence, like a shaded pole, a notch, or a small asymmetry in the armature's magnetic arrangement. Once it's spinning, the rotor's inertia keeps it moving in sync, perfectly timed with the power line itself. That's the beauty of synchronous motion: precise, predictable, and in perfect harmony with the AC cycle. I'm Steve from the Tech Circuit. For more demonstrations of electrical theory like this, don't forget to subscribe.